So how did you write the equation of the line back in grade 10? What do you remember? Right? Y equals mx plus b. And in order to write an equation of a line, you needed to know what the slope was or be able to find it. And you needed one other point so that you could figure out what the y-intercept was. Or if you had that other point, then you might have even written the equation in the point-slope form. So those are two little reminders of what you learned way back in grade 10. So now, what an equation of a line did in grade 10 is it told you all the points that could possibly be on that line. So if you had y equals 3x plus 2, when you plug in 0, you get 2. When you plug in 1, you get 5. And you could get all these points and connect them all. The idea with the equation of a line in vector form is so there's that line, y equals 3x plus 2. What we're going to do, instead of saying my equation gets me all the points, instead we're going to say my equation can get me all my position vectors. In other words, instead of saying the point 0, 2, we're going to call that the vector that looks like this. And this point here is going to be this position vector. So every single point that's on our line, we're going to have a position vector for that point. So what does that look like? Well, here's a diagram. This ARC is our line that we want to make an equation for. What we can do is we can find any position vector, and we're going to show that by position vector r. So here's a random point r on the line, and we have a position vector for that. So we get the following equation. Any point on that line, which is our position vector r, is going to equal any other random point on the line. So A is another random point that's on the line, and we have a position vector for A right here. And if you wanted to find any other point on that line, all you have to do is get to point A and then go a certain distance in this direction, either this way or this way. Well, if we're going in that direction, we're going to need a direction vector. In other words, we're going to need to know what the slope of that line is. If we can find the slope of that line, we can basically say that's its direction vector. So if we had another point on our line like point C, then you could do negative a plus c to get the direction vector, which is basically like our slope. And once we've got point A and the direction that we're going in, we just have to say some parameter to tell how far in that direction you want to go. So I get to point A, and then I know this slope, so I can go in either direction. If I want to go to point R, I just have to go in that direction a certain distance, and I'll get there. So what we do is we write our vector equation. Instead of writing the c minus a, we actually get that as a direction vector b. We calculate it. T is some scalar that tells us how far we travel in that direction, and then we get our vector equation of our line. So to recap, A is a random point on the line, and the vector r is the way that we can find all points on the line. So the difference between y equals mx plus b as a Cartesian point thing and r equals a plus tb is the b, if you're making connections, acts very much like your slope. But instead of a being a y-intercept, this equation allows it to be any point. So So you've got sort of the same idea as y equals mx plus b, but your b is like your slope, but a is any point, any random point on your line. So we can take this equation, and in 2 dimensions, you've got an x and a y point. That's your r. That's your random point on your line. You've got a, which is another, or x and y is any point on the line. You've got a, which is a random point on your line, and b, which is your direction vector. And so if you write these as column vectors, this is what your equation looks like, where this is your r, this is your a, and this is your b. And then we have a parametric form. The parametric form is just looking at specific coordinates. The x coordinate is equal to a1 plus t times b1. The y coordinate is the a2 plus t times b2. And in each of those parametric forms, you can rearrange them and get t by itself. Some simple algebra, you'd have to subtract a1 on both sides and then divide by b1, or subtract a2 on both sides and divide by b2. And since both of those are equal to t, you can rearrange them and put them together, and you get your Cartesian form. So what we're going to look at is each of these forms are helpful in different ways. The Cartesian form is the way to link it back to y equals mx plus b if you wanted to do that. The parametric form is going to help us solve some problems later on where that's an easier way to break it down. And then the vector equation is just the general equation. So we're going to start with a vector equation line passing through the point 2, 5 and parallel to the vector 3, negative 4. So you start off with our vector equation line. A, R, and B are all vectors. So we need a random point on the line. Well, we have that. That's 2, 5. Since it's parallel to 3, negative 4, and this vector, if you wrote it as a column vector, 3 in the x direction, negative 4 in the y direction, would look like that. So that becomes our direction vector, and we just need to write it like this. Now we can write the parametric and the Cartesian forms. So the parametric forms, you're just going to look at the x coordinates, so 2 plus 3 times t. You're going to look at the y coordinates, 5 plus a negative 4t, or 5 minus 4t. Can you see that you could get t by itself in the first one by subtracting 2 and dividing by 3? Can you see that you could get t in the second one by subtracting 5 and divided by negative 4? So your Cartesian form is just equating those two. So now if you wanted to reconnect this to your grade 10 math, now that you've got this Cartesian form, can you see that you could sort of cross multiply to get rid of the fractions? If you did that and rearrange things, you could get it in y equals mx plus b form. The slope is going to be negative 4/3. Now slope is rise over run. So slope is always your y values on top but your x values on the bottom. Whereas if we go up, our direction vector always has x on the top and y on the bottom. But you see the negative 4/3 there if you flip that around. So it's very similar to your slope. Okay? If you were using y equals mx plus b, you'd have to work with negative 4/3 and 23/3. Working with vectors, you're just working with those whole numbers all the way through. So it's a little bit nicer that way. if you had solved this using your grade 10 math, you would have had your slope as -4/3. You would have had your point. You could have plugged it into your point slope form and rearranged and solved for y to get y equals mx plus b that way as well. Or you could have started off with y equals mx plus b, plugged in the point 2, 5 for x and for y and solved for b, and you would have got 23/3 that way as well. But what we're going to find is our vector equations are more simplistic to work with once you get used to them, because you're not dealing with all those fractions. So now we want to find a vector equation line passing through that same point, perpendicular to the vector 3i plus j. So that vector is 3, 1. Does it make sense that its slope then is 1/3? And then if you wanted to do the slope of a perpendicular line, you'd have the negative reciprocal. So you would flip it and make it negative. The same thing's going to happen with a vector. If that's my direction vector and I want to find it perpendicular, I just need to flip it and make it negative. It doesn't matter which coordinate you make negative. So you could have what I have here as 1, -3, or you could have it as -1, +3. Now, just to think about that, if I have 1, -3, can you see that would be going 1 in the x direction and 3 in the y direction? That would be 1, -3. If I had -1, 3, that would be 1 this way and then 3 up. Notice that they're on the same line. They have the same slope. They're just going in different directions. So depending on which one you use will affect how your t-value has to get to a point. Right? If I needed to go in this blue vector direction, then my t-value would be positive. But if I was using the green vector, then my t-value would have to be negative to flip it to go the other way. So you just need a point on your line, your direction vector. You can write the parametric forms by looking at just your x and y coordinates. And you can look at your Cartesian form by solving for t and making them equal. So for this equation, you've got 2 points, but you're not given the direction vector. But if you draw a little picture of this, A is at 1, 4, so that would maybe be about there, and B is at 5, 8. There's AB. How do I get vector AB? I know vector A, I know vector B. So I can just go back to the origin and then to B, and that will give me vector AB. Well, how do I do that? Back to the origin would be -A. And then once I'm at the origin to get to B, that would be plus B. So from A to B will be -A plus B or B minus A. And if you just write those as 5, 8 minus 1, 4, you get your direction vector to be 4, 4. What would that be as a slope? Can you see that that would be 4/4? That you could write it as 1/1, or 2/2, or 3/3? So for your direction vector, I mean, if you come up with 4, 4, it's most likely that you'll write 4, 4 as that direction vector. But it would be also correct if you had any, let's say, equivalent slope there. So if you had 1, 1, or 2, 2, or 3, 3, that would be fine. And then the point A is any random point, so you could have chosen 1, 4, or you could have chosen 5, 8. Then whichever one you've chosen, you can write your parametric and your Cartesian forms from that as well. So here we were given 2 points, and we wanted to find the equation of the line passing through those 2 points. Well, there we get our direction vector from finding that vector AB, and then we use any of the 2 points to get your random point. Same idea in 3 dimensions. Nothing really changes other than your column vectors will now have 3 things. So if it passes through P and Q, you can find PQ by just going Q minus P. And that'll be your direction vector. So to write your equation, you need to take one of your 2 points. So I just chose the first one here, 1, 5, 3. By doing Q minus P, 2 minus 1 is 1, 0 minus 5 is negative 5, negative 4 minus 3 is negative 7. To get our direction vector. And then plug things in. So for vectors, to do really well on vectors, you really just have to take the time to understand what do the different parts mean. Right? One, I have a direction vector. How do I find a vector between those 2 points? I can do that by just subtracting them and then writing out that equation. So now the question is, does this point lie on that line? Or is it just a little bit off? Well, if it does lie on that line, then there would have to exist some value t that you could go in that direction vector and get to that point. So if we look at each of our parametric equations, and so this is where our parametric equations become very helpful. If we look at the x-coordinate, the y-coordinate, and the z-coordinate, in each of those we could solve for t. And here we get t is equal to negative 2, t is equal to 2/5, and t is equal to negative 2/7. In order for that point to be on the line, it would have to get there at the same time. And so here, since those t values are all different, we can say that no, it does not lie on the line. We can get to each of those coordinates at a different time, but we can't get to that point at the same line. So our parametric equations really help us solve for t. And in order for something to be on the line, there would have to exist a value t that worked for all 3 of those. So what's your guess for 3, negative 5, 5? Is it going to lie on the line or not? Gut feeling before we solve it. Set up our parametric equations. And t equals 2 on the first one, t equals 2 on the next one, and then, negative 2/7 on the third one. And this was my attempt to be an unpredictable teacher. Because what does a teacher normally do? Show one case in one example, the other case in the other one? How many of you were predicting that this one would be on the line? Come on, admit it. You've been in school for way too long. You're able to predict teachers. Anytime that the t is not the same, it is not on the line. If this last value had been negative 2/7, I believe it would have worked. Is that right? 3 plus 2 times, no, it would have to be 2 times negative 7 is negative 14 plus 3. If this was negative 11, it would have worked. But it wasn't. Sometimes we get vector equations of the lines to look like this. This is kind of like parametric equations, because what they're basically saying is, well, your random vector is x, y, or your vector. Can you see the parametric equations built in this way? So we could write this as a vector equation. You'd have your vector r. You've got your random point on that line, 3, 5, and then the 2, negative 5 is your direction vector. And now we can review some stuff. What is a unit vector? A unit vector has a length of 1. That was one of the first vector lessons that we did. So if we want to find a unit vector, we need to find out how long a vector is, and then divide by that to make it a length of 1. Now, if we want it in the same direction as L, you now have a choice. You have to make it, or not a choice. Choice means either one is the right answer. You have a decision. One of them is going to be the right answer. One of them is going to be the wrong answer. You need to find a unit vector, and you're either going to choose the 3, 5 or the 2, negative 5, because those are the two vectors you have. Which one do we want to choose? Which is the right decision if we want to find the unit vector in the direction of L? Okay, you've thought about that. If you want to find it in the direction of L, you would want to use your direction vector. So the length of 2, negative 5, square root of a squared plus b squared will give you the square root of 29. And then your unit vector will equal this, or if you'd like, I often prefer to write it like that. That way you keep that nasty square root out of all of your calculations till the very end. And since we've found our vector equation, we can rearrange it to get our parametric. And once you have your parametric, you can solve for t and get your Cartesian form. So we have two lines, line RL and line RM. So lines L and M have these vector equations. So again, it's just another form of writing the same thing. Can you see the parametric equations here? Remember that I is always with your x coordinates, j with your y, and k with your z. So your parametric equations here, this one's x equals this, y equals this, z equals this. X equals this, y equals this, z equals this. So as far as rewriting our points are concerned, nice. There, I'll do this. No, that was bad. Okay, I'll just rewrite them. So as far as rewriting our points are, we can say that this first equation has the point 5, 3, and 0, plus our parameter is s, and we've got -4, 1, and 2. I personally always like to rewrite my vector equations in this form because I feel it's the easiest to visualize. I can easily see that those are the points on my line, and this is my direction. So in that second line, can you see that direction for the z is 0? That there's no t at all in this last one. Can you see that there's no point in our line L for our z coordinate? So here we have our vector equations, and from our vector equations, we can get two sets of parametric equations. You have your parametric equation from your first line and your parametric equations from your second line. Now, if they have a point in common, does it make sense that the x's would equal, the y's would equal, and the z's would equal? And so if you make your x's equal, your y's equal, and your z's equal, you would have equations with s and with t. Now, often, you'll then have to solve a system of equations. However, if we look at all three of those, the x, the y, and the z, can you see that the z one works out really nice because you'll just get 6 is equal to 2s. And from that one, you don't even have to solve a systems of equations. But from that one, you find out that s is equal to 3. So if s is equal to 3, you can plug that in and find out what y and what z would equal to. If you wanted to, you could also figure out that t would have to equal 1. And so we have our common point. Your x is -7, your y is 6, and your z is equal to 6 as well, which it has to be because z is always 6 on our second line. And that's the point that intersects. So as far as finding a common point is, this is the easiest one because there was something right away, that z coordinate, where you could solve for one of your parameters really easily. If this question comes up on your exam, I would predict 90% of the time you would have s's and t's in all three of them, and then you'd have to choose two of them and make a systems of equations and solve for s and then solve for t, and then plug that s and t value in to all three of your equations to find out if they're the same. So now we found a common point. We can now find the angle between these lines using what you learned about the dot product from last class. Okay, so here's our two lines. If you're finding an angle between them, you have to make a decision which vectors you're going to use. Remember, the first vector is just a random point on the line, and the vector with the parameter is the direction it's going. So if you're wanting to find an angle between two vectors, you're going to have to look at their direction that they're going, not just a random point. Choosing -4, 1, 2, and -4, -1, 0, I have seen on final exams choosing the right vectors being worth 2 marks. That this question on its own I've seen worth up to 7 marks. And they give a lot of marks for little things. So I'll give you a mark scheme of how this could be worth 7 marks in the end, or maybe 6. We'll see how much. So you need to first decide to use your direction vectors. And our formula, cos theta, is u dot v over the magnitude of u times the magnitude of v. So the dot product, multiply the corresponding coordinates, and then add them all up. Negative 4 times negative 4 is 16. 1 times negative 1 is negative 1, and 2 times 0 is 0. And then finding the length of each of them, a squared plus b squared equals c squared, and then taking the square root. And you get cos of theta is 15 over the square root of 21 times the square root of 17. So you'd have to do cos inverse, and if you were in degrees, you'd get 37.5 degrees. If you were in radians, you get 0.654 radians. So unless the question explicitly says degrees or radians, both would be fine. More often, for what we're doing, you'll see degrees with your vector equations. But both would be fine. So, how is this worth 7 marks? Well, first of all, see, you get 1 or 2 marks for choosing the right vectors in each one. Then you get 1 mark for showing your work of the dot product. 1 mark for getting the answer. 1 mark for each of the lengths. So we're already at 6 marks. And 1 mark for doing cos inverse and getting your answer. So a lot of marks, a lot of easy marks. If you choose the wrong vector to begin with, if you choose one wrong vector, let's say you don't choose this one, you don't get that mark. Your dot product is now not correct, you don't get those 2 marks. One of these won't be right, you won't get that mark, and your answer in the end won't be right. Choosing one vector wrong at the beginning might be a silly mistake, and you might know how to do everything else after that, but the IB marking, where it doesn't follow through within a question, you start losing a lot of marks. It could be that you only get 2 out of 7 as a result. So it's really important that if you're finding the angle between 2 lines, that you know that you must choose those direction vectors to begin with. Because if you choose the wrong vectors, it can be sort of catastrophic in a 7-mark question, which should be 7 fairly easy marks.